So what I was showing you in the previous video was problem 1 from your homework, where you get, when you go look at this polynomial in lambda, you get a polynomial with 2 distinct real roots. That's like the easiest situation you can have. So we got these 2 distinct real roots, 2 and 3. Sorry, it was this one. We got 2 distinct real roots, 2 and 3. Here's where the work was, 2 and 3, and we got these eigenvectors to go with them. I think I'm just going to scroll through the other homework problems, since I basically made these homework problems to show you the different things that can happen. So let's look at problem 2. And I'm just going to use Mathematica to sort of skip over some of the boring parts of the calculation. So I'm going to type in the matrix. Okay, so there's the matrix. And then what I'm going to be interested in is the determinant of the matrix minus lambdas along the diagonal. So this is the matrix. I'm just subtracting from it the matrix lambda 0, 0, lambda. So if you want to look at what this looks like in sort of pretty form, you can do matrix form. So basically this, right? Take this matrix, subtract lambdas from the diagonal, and then examine the null space of this thing. The null space of this thing would be the eigenvectors. First of all, we want choices of lambda that make this have an interesting null space, a non-trivial null space, right? So those will be the choices of lambda, the very, very few choices of lambda that would actually make this have determinant 0. So let me take the determinant of this thing. So this is determinant with a capital D function. And this is the polynomial that I get. So 2 lambda plus lambda squared. What are the roots of that? So you can write it as lambda times 2 plus lambda. So it looks like the roots are lambda equals 0 and lambda equals negative 2. So this matrix has 2 eigenvalues, lambda equals 0 and lambda equals negative 2. And remember I said that 0 should not be allowed as an eigenvector, right? Because with eigenvectors we want, where'd it go? With eigenvectors, the v part of this, we want it to communicate a direction, right? An eigenvector should be a direction along which the behavior of a matrix is simple. 0 is not really a direction. So we don't allow v equals 0, but lambda equals 0 is perfectly fine. So there just happens to be a non-zero v for this particular matrix. Where'd it go? Oh, I never wrote it down. For this particular matrix, negative 6, negative 12, 2, 4, there just happens to be a non-zero v. I don't know what it is yet. A non-zero v such that a times v is 0 times v. Or in other words, a times v is 0. So there's nothing wrong with having 0 as an eigenvalue. That just tells you that the matrix already, even without subtracting anything from here, subtracting 0, the matrix already had an interesting null space. Okay, so that's all I'm really showing you there. Let's look at another one. So here's one with repeated eigenvalues, and it's actually already sort of in diagonal form, so that makes it even easier. So you can immediately, just from staring at this, you immediately know 1, 0, and 0, 1 are eigenvectors, right? But let's just proceed blindly and look at what the characteristic polynomial. Oh, I never used that word, by the way. So this when you do this polynomial in lambda, this is called the characteristic polynomial of the matrix. So yeah, when I subtract lambda identity from a and I take the determinant, I get this thing, and it looks like Mathematica has already expanded it for me, but it started out factored and it was like this, 4 plus lambda squared. So this polynomial has repeated roots, negative 4 and then negative 4 again. But there's no problem. I mean, you can just say the eigenvalue -4 has two eigenvectors. So it's kind of like, we started with this, we solved determinant or whatever equals 0, and then we got -4 twice, and then we just found actually two linearly independent eigenvectors. 0, 1, 0, and 0, 1 work perfectly fine, and they're linearly independent. There's nothing wrong with that. What does this matrix do? Well, if you write out a vector in terms of, as a linear combination of these two, 1, 0, 0, 1, then it will multiply the first component, the first coefficient, by -4, and the second coefficient by -4. Actually, for this one, we could have put any vectors we want here, any two linearly independent vectors, and that would be an equally good description. So this is just a really simple situation. But that's not always what happens when you get repeated roots, and I think I set up problem 4 here to show you what can go wrong when you have repeated roots. So this will be a case where you'll find there's actually just one eigenvalue. So here, if you get the characteristic polynomial for this, you'll see it has repeated roots, but you will only be able to find one vector in the null space of A minus lambda identity. Whereas with problem 3, if you just blindly do the calculation, even though you can see the answer staring you in the face, if you just blindly do the calculation anyway, write down A minus lambda identity, where lambda is -4, and then try to find the null space, well, you're looking at the 0 matrix. So you can find two linearly independent vectors in the null space. In this one, you only find one. So this is where things go wrong with repeated eigenvalues. And let's see, problem 5 and 6. Okay, 6 should be easy. Just this is what we've been doing on the board here. Yeah. So let me just finish going through 6. So if you have matrix A and you know about the eigenvectors and eigenvalues, then when you write something as a linear combination of the eigenvectors, then you know what A does just from this information, right? Just distribute A, and then you know how it operates on the eigenvectors. So that's easy. And then problem 5 is maybe the most complicated situation. So this is where complex numbers show up. So this is like the third case. When you look at a polynomial, a quadratic polynomial, you could have two distinct roots, repeated roots, or complex, no real roots, complex non-real roots. So the good news is to handle this one, just go with it and do the complex algebra. So if you're comfortable just doing stuff with complex numbers, you don't really need to know anything more. Just go with it. Just do it. But just in case that's, I imagine that's not necessarily something everybody's super familiar with as much as working with real numbers. So how about I make the next video be about doing this one?